Good day, everyone. So we're reviewing Wetzel's Limnology textbook, edition number 4. We're on chapter 15, and we're looking at phosphorus and eutrophication. Combination of many physical and biological variables as regulating trophic states have clouded true cause and effect relationships of rates of primary production. As Carlson and Carlson-Simpson emphasized, the trophic state concept is important as a critical organizing concept in limnology. The concept represents a continuum of trophic levels that is difficult to quantitatively delineate into trophic state subgroups, but is done so nevertheless. Organization along a trophic continuum is but one facet of lake typology and uses biomass or rates of production as the simplest and most useful definition of the trophic state. Many variables can be evaluated in the context of algal productivity, for example, phosphorus loadings and concentrations, chlorophyll A concentrations, as a proxy of phytoplankton biomass, phytoplankton productivity, phytoplankton biomass, hypolimnetic oxygen deficits, transparency, etc. The annual mean rate of production is an excellent criterion but requires intensive and sophisticated methods for determination, and thus is generally not included in routine monitoring programs. Biological food web structure is highly susceptible to change along dynamic environmental gradients other than nutrients. Hence, it differs greatly globally. Therefore, no portion of the biological structure other than primary production or its proxy is recommended as a criterion of the trophic concept. Nevertheless, certain ecological changes such as the formation of harmful cyanobacteria blooms, loss of macrophyte beds in shallow systems, or loss of cold water fish species in deep lakes due to loss of hypolimnetic oxygen are often noted as hallmark characteristics of a eutrophic state, where the risk of these occurring increases with increasing phosphorus concentrations. The relationship between nutrients, loading, and productivity in aquatic ecosystem B. Great emphasis has been placed on nutrient availability in regulating aquatic productivity, especially phosphorus, since the majority of oligotrophic lakes and many eutrophic lakes are phosphorus limited. Strong linear and sigmoidal log and log correlations between chlorophyll A and total phosphorus, along with numerous whole lake fertilization and bioassay experiments, are evidence of the causal nature of this relationship. As will be discussed later in treatments of biological productivity, many non-biological factors other than phosphorus and nitrogen can regulate productivity, such as temperature, light, and lake morphology. The early analysis of differences in productivity among aquatic ecosystems focused on differences in nutrient concentrations. Increased information gradually demonstrated the rapid dynamics of the exchange of nutrients among algae as nutrients were assimilated, utilized, and released during and following growth, reproduction, and death. Still among these studies, however, a prevailing concept was to treat lakes as closed, self-sustained entities. The most rapid change in these viewpoints arose largely in the late 1960s and 70s, with full recognition that rivers, and particularly lakes, are open systems critically dependent upon coupling with their drainage basins. Phosphorus and nitrogen had been recognized for several decades in agriculture as critical nutrients that often limit plant growth and productivity, and they were similarly recognized in phytoplankton productivity. The importance of phosphorus and nitrogen in the eutrophication of surface waters was also long recognized, but with the understanding that lakes are open systems, it became apparent that the rates of loadings of these nutrients from the drainage basin were critical to trophic conditions. From a management viewpoint, one could also define loadings of nutrients in terms of whether they were acceptable or excessive in terms of the algal productivity generated under the lake conditions of morphometry and water retention times. The trophic categories of oligo, meso, and eutrophic were gradually analyzed in increasingly quantitative ways in terms of nutrient concentrations, phytoplankton biomass, chlorophyll A concentration, and water transparency, in addition to the classical characterization of hypolimnetic oxygen concentrations. These data from many lakes allowed the development of dynamic, quantitative modeling for the prediction of probable biotic conditions as a result of nutrient loadings from the drainage basin. A summary of these relationships developed and extensively tested in the 1980s is presented later. In more recent time, much attention has been directed to the internal recycling of nutrients within lakes and streams. In particular, internal loadings of nutrients from accumulations in sediments have been examined to determine how this recycling of nutrients supplements those allochthonous sources from the drainage basin and atmosphere. In addition, as is summarized in this chapter, much attention is directed to the recycling of nutrients through food ingestion and alteration by animals. Effects of phosphorus concentration on lake productivity. The consensus among limnologists is that the term eutrophication is synonymous with the increased production of the biota of lakes, and that the rate of increasing productivity is accelerated over that rate that would have occurred in the absence of perturbations to the system. The most conspicuous, basic, and measurable criterion of accelerated productivity is an increased quantity of carbon assimilated by algae and larger plants per given area. Under most lake conditions, the most important nutrients causing the shift from a lesser to a more productive state are phosphorus and nitrogen by virtue of their high cellular content, although other metabolically essential elements such as certain trace metals may also limit productivity. Typical plant organic matter of aquatic algae, cyanobacteria, and macrophytes contain primarily phosphorus, nitrogen, and carbon approximately in ratios known as the CNP, Redfield's ratio, which are 41.6, 7.3, 1.0 by weight, or 106, 16, 1 molar. With smaller amounts of sulfur and trace metals. These CNP ratios are relatively constant in marine plankton, but are more variable in freshwater systems, depending upon luxury uptake and growth rates. A comparison of the relative amounts of different elements required for algal growth with supplies available in freshwater illustrates the general importance of phosphorus and nitrogen. Similar proportional ratios were demonstrated by comparison of the demand among terrestrial plants with the accessible supply of elements from the lithosphere. Even though variations in conditions that affect solubility or availability may at times make elements that are normally very abundant in Earth's crust almost unobtainable, phosphorus and singularly nitrogen most frequently impose limitation on aquatic systems. This relationship is emphasized further by the consideration of average demand-supply ratios in late winter prior to the spring algal maximum common in lakes of temperate region and in midsummer during maximum sustained algal productivity. Oligotrophic lakes are usually limited by phosphorus and contain nitrogen in quantities in excess of demand from growth, supported by available phosphorus. As the lakes becomes more productive, the primary affecting agent is increased loading of phosphorus. As discussed earlier, the instantaneous concentrations of phosphorus usually decrease and are quite variable, but the turnover rate increases markedly. Rates of loss of increase and high algal productivity requires sustained phosphorus loading of the system from allochthonous and littoral sources. So let's look at these tables here. Table 15-15, comparison of the ratios of required concentration of inorganic nutrients to average supplies available in fresh waters. So on the left we have the elements, phosphorus, nitrogen, carbon, iron, silicon, etc. Then we have the ratio of demand to available supply. So for phosphorus, we can see that it's the most limiting factor out of the ones listed here. We have 80,000 up to 800,000 in the midsummer, which is the most productive time for plant biomass. Nitrogen, we have 30,000 up to 300,000, so it's a factor of 10 for all of them here, and even higher for carbon. But still, phosphorus leads the pack in terms of the ratio of demand to available supply. 15-14, we have proportion of essential elements for growth in living tissues of freshwater plants in the mean world river water, and the approximate ratio of concentration required to those available. So this is for rivers, not for lakes. We have the elements on the left, and then we have the value in terms of the the value of the specific atom in percentage for these for living tissue of freshwater plants. And then the average supply is in the water, and then the ratio of the plant content to supply available. So where, for example, like carbon, we have average plant content of 6.5, and average supply in the water in percentage is 0.0012, and so we have a factor of 5,000 between what is available in the river water compared to what the plant finds in its tissues. So let's look at phosphorus. So phosphorus, we have a pretty low value in the tissues at 0.08, but we have even lower values in the water supply, and then we have a demand here of 80,000 for phosphorus, which we found here in late winter, by the way. It's kind of correlated, it appears. And then atoms that are very poorly represented in tissues of plants, for example, cobalt, we have 0.000002, so 2 by 10 to the minus 6, and then here we have probably like 1, 2, 3, 4, 5, 6, 10, 5 to 10 to the minus 8. So we have a factor of 100 between what is available in plant tissue to what is available in waters. And then the ratio of supply to demand is greater than 1,000 for a lot of those. Some studies have indicated that nitrogen rather than phosphorus is limiting to non-fixing phytoplanktonic productivity of lakes, at least in certain water strata and at certain times of the year in phosphorus-limited lakes. Most oligotrophic lakes globally are phosphorus-limited, but nitrogen limitation is common in, for example, the American Great Basin and northern Sweden. Diazotrophic cyanobacteria are only nitrogen limited when nitrogen fixation is a resource limited, for example, by a trace metal enzyme cofactor such as molybdenum or by phosphorus. So, as we saw earlier, cyanobacteria fixes atmospheric nitrogen into ammonia and uses that to thrive and to build amino acids, for example. And as we know, nitrogen is pretty abundant in the air. I think it's in the order of 70 percentile. And however, that's not the limiting factor. What would be the limiting factor is that atom, the molybdenum or biphosphorus that are found in this metal enzyme cofactor that helps the cyanobacteria to fix nitrogen from the atmosphere. When phosphorus is available in quantities in excess to support metabolism, nitrogen availability can become limiting to non-fixing biota. This limitation is often observed in the two extremes of the trophic spectrum. Under eutrophic conditions of high phosphorus loading, planktonic utilization of combined nitrogen can exceed inputs and literally deplete combined nitrogen supplies in the trophogenic zone in a few days or weeks. When this occurs, nitrogen fixation by heterocystus cyanobacteria can augment the nitrogen inputs to the lake, although it may be insufficient to alleviate nitrogen deficits in non-fixing biota. Although the metabolic cost is high, cyanobacteria growth rates and biomass yields in batch cultures are relatively unaffected when trace metal supplies are adequate. In tropical lakes of low altitude, nitrogen limitation to phytoplanktonic growth can occur. Phytoplanktonic productivity of tropical waters is generally higher than at temperate latitudes, and higher temperatures can accelerate rates of denitrification and losses of nitrogen to the atmosphere. Under oligotrophic conditions, phosphorus availability may be adequate to support modest levels of phytoplanktonic productivity, but sources and loadings of combined nitrogen are insufficient to support such productivity. Increasing the availability of nitrogen can result in increased algal photosynthesis under phosphorus again becomes limiting. Enrichments with both nitrogen and phosphorus can stimulate algal productivity markedly. Phytoplanktonic productivity of reservoirs often fluctuates to a much greater extent than in natural lakes because of the frequent variation in inorganic turbidity In some reservoirs, the limiting effect of light penetration on photosynthetic activity can be more severe than that on nutrients. Nutrient loading to reservoirs from external sources can vary with long-term precipitation patterns and water inflows in comparison to the volume of the productive zones. If flushing rates are high, turbidity can increase, but also nutrient loadings and availability can increase. Hypolimnetic withdrawal can also affect concentration by discharging internally loaded phosphorus downstream. The potential for limitation of eutrophication by inorganic carbon availability has been a subject of much discussion. In a few exceedingly productive situations, such as sewage lagoons, in which phosphorus and nitrogen compounds are available in excess of any demands, carbon can become limiting to algal growth. While there is some evidence for inorganic carbon limitation in exceedingly soft lakes, diffusion of atmospheric CO2 is generally adequate to sustain the carbon requirements of phytoplanktonic population in eutrophic lakes. It is extremely unlikely that carbon limitation is of significance in the limitation of algal populations in the majority of harder waters in which dense algae develop under eutrophic conditions. The importance of phosphorus in comparison to nitrogen and carbon has been particularly well illustrated by large-scale fertilization experiments. Lake 226, located in the experimental lakes area of northwestern Ontario in Precambrian shale bedrock, was chemically and biologically similar to greater than 50% of the waters draining to the northern Laurentian Great Lakes. Lake 226 was partitioned with a large plastic curtain into two basins at a constriction in the lake. One basin was fertilized with phosphorus, nitrogen, and carbon, and the other with equivalent concentration of nitrogen and carbon, made in 20 equal weekly increments. The NP and CP ratios were greater than in treated sewage, but the quantity of phosphorus added was not exceptionally high for lakes that commonly receive pollution from domestic sources. The phosphate-enriched basin quickly became highly eutrophic, while the basin receiving only nitrogen and carbon remained at pre-fertilization conditions. In this phosphate-enriched basin and in several other lakes, receiving analogous treatments over a period of several years, algal biomass increased to 2 orders of magnitude over that of lakes receiving only nitrogen and carbon enrichment. Recovery to near pre-fertilization levels was very rapid when phosphate additions were discontinued. Lake 227 was the site of a 50-year experiment between 1970 and 2020 at a constant phosphorus fertilization rate, receiving nitrogen as nitrate for the first 20 years and only phosphorus for the last 30 years. The lake remained highly productive 30 years after nitrogen addition stopped, with increasing inputs from nitrogen fixation as legacy nitrogen was depleted. A distinct issue, but one related to increased productivity, is the displacement of eukaryotic algae by diazotrophic cyanobacteria during blooms for short periods of time in nitrogen-limited eutrophic systems, that is, systems with excessive phosphorus inputs relative to nitrogen inputs. In this system, mean phytoplankton productivity during the ice-free season will be nitrogen limited, but cyanobacteria productivity will not, by virtue of their nitrogen fixing ability, as long as trace metal cofactors supply molybdenum and iron for the nitrogen fixing enzyme nitrogenase are adequate. Note that some species are not fixers but will not dominate blooms in nitrogen limited systems. It is important to distinguish between mean daily ice-free phytoplankton productivity, which includes eukaryotic algae and cyanobacteria bloom productivity, and daily productivity during a bloom. The latter will be higher than the ice-free daily mean because of nitrogen fixation input during the bloom. For example, in nitrogen-limited Lake 227, a month-long nitrogen-fixing aphanizomenon bloom occurred every summer during the 30-year period of phosphorus-only fertilization, with a large biomass peak during the bloom. In another experiment at the experimental lakes area, oligotrophic lakes 303 and 304 were also fertilized weekly with only phosphorus, producing dense month-long blooms of nitrogen-fixing Dolichospermum feces in both lakes within 9 to 12 weeks after fertilization began, turning the lakes visibly green without the addition of nitrogen. Nitrogen fixation doubled the nitrogen content during the blooms, hence reporting the mean daily ice-free average of, for example, chlorophyll A without reporting chlorophyll A during a cyanobacteria bloom will obscure the size of the bloom within the seasonal average, which may affect eutrophication management choices. These results suggest that many nitrogen control programs are unlikely to mitigate cyanobacteria blooms, although they may lower cyanobacteria toxicity and eukaryotic biomass. Phosphorus control should remain a cornerstone for cyanobacteria management. The amount of evidence for the phosphorus-chlorophyll-A relationship is so overwhelming, both from experimental and applied investigation, that it is difficult to appreciate how the bitter controversy over the importance of carbon rather than phosphorus as a limiting nutrient in fresh waters developed in Canada in the late 1960s. As a result of the combination of the magnification of a few findings from cyanobacterial cultures and a few rare cases of discovered low carbon availability in natural habitats in which excessive amount of nitrogen and phosphorus occurred, phosphorus was implied to be of less importance in the acceleration of eutrophication than carbon. So convincing was the misinterpretation of results by a few scientists, and so effective was the exploitation of the situation by the detergent industry and irresponsible journalists that legislation was urgently needed to reduce the effluent loading of surface waters with phosphorus was seriously impeded. The matter was finally put to rest by the The matter was finally put to rest by the rebuttal of Valentine, numerous subsequent investigations, and a national symposium on the subject. And that will be completing my presentation to today's phosphorus on eutrophication. And I will see you tomorrow, where we will go over the stoichiometry of carbon, nitrogen, and phosphorus in particulate organic matter. Thank you, and have a good day. Bye.